Hi all. Today in this lecture we will discuss about distance vector routing. In datagram network or IP network, routing is an issue for every packet. A switch or router needs to look at the packet destination address and then to determine which of the output port is the best choice to get the packet to that address. Switch makes this decision by consulting a forwarding table. And the fundamental problem of routing is how do switches and routers acquire the information in their forwarding tables. So, these routing algorithms are used to construct these forwarding tables. And before going to distance vector routing, we had to make an important distinction between forwarding and routing. Forwarding is the process of taking a packet, looking at its destination address, consulting a table, and sending the packet in a direction determined by that table. Whereas routing is the process by which forwarding tables are built. The basic problem of routing is to find the least cost path between any two nodes where the cost of the path equals the sum of the cost of all the edges that make up the path. So coming to distance vector routing, as the name implies, the metric used here or the cost used here is the distance between two nodes. And the least cost route between any two nodes is the route with the minimum distance. Each node contributes a one-dimensional array containing the distances to all other nodes and distribute that vector to its immediate neighbors. The starting assumption is that each node knows the cost of the link to each of its directly connected neighbors, and a link that is down is assigned an infinite cost. To see how this algorithm works, let us consider an example. This figure shows a network with 5 nodes A, B, C, D, and E, and the table for node A shows how we can reach any node from this node, and this table consists of mainly 3 columns. The first column is the destination, second one is the cost to reach the destination, and third one is the next hop. So initially, the first step is the initialization step, and initially each node sends a message to its immediate neighbors and find the distance between itself and these neighbors. And the distance for any entry that is not an immediate neighbor is marked as infinite. So here in initialization step, we can see node A is directly connected to B, C, and D. And the distance to these nodes are written as from node A to B 5, A to C 2, and A to D 3. Whereas node E is not directly connected to A, or it is not an immediate neighbor of A, so the distance to E is written as infinite. Similarly, an initialization table is maintained for a node B, C, D, and E. Here D is not an immediate neighbor of B, so distance to D is noted as infinity. Similarly, for C, node D is not directly connected and distance to D is noted as infinity. And for D, C and E are not directly connected. B is also not directly connected, so distance to these three nodes are noted as infinity. And for E, A and D are not directly connected, so distance to these two nodes are denoted as infinity. So So this is the first step. This is the initialization table for node A, B, C, D, and E. The next step is sharing. What actually takes place in sharing is each node shares its routing table with its immediate neighbors periodically and when there is a change. There is a change means when there is a change in the network topology due to any node failure or some other problems. So in sharing, actually we note that node A doesn't know how to reach node E, isn't it? But node C knows it. Similarly, node C doesn't know how to reach node D, but node A does. So, when in the second step, when each node shares its routing table with its immediate neighbors, they came to know how they can reach the other nodes. So, using that information, they can update their routing tables. So, here node C tells node A that it can reach node E at a cost of 4 and A also knows that it can reach C at a cost of 2. So it adds these costs to get the cost of reaching E by means of C. That is, to reach E from A can reach E through C at a cost of 6. So in the final step, this value of 6, which is less than infinity, is recorded and this value is updated. Similarly, coming to B's table, we can see that B is not directly connected to D, but when B receives node A's table, node A tells B that A can reach D at a cost of 3 and B can reach A at a cost of 5. So B can update its routing table that B can reach D through A at a cost of 8. So these values are updated in the table, and the last step is the updating. So in updating, when a node receives a 2-column entry from a neighbor, it needs to update its routing table, and this updating takes in 3 steps. The first one is the receiving node needs to add the cost between itself and the sending node to each value in the second column. The receiving node needs to add the name of the sending node to each row as the third column if the receiving node uses information from any row. The receiving node needs to compare each row of its old table with the corresponding row of the modified versions of the received table. If the next node entry is different, the receiving node chooses the row with the smaller cost, and if there is a tie, the old one is kept. If the next node entry is the same, the receiving node chooses the new row. And this is the final table for this network. So these are the shortest least cost path, shortest distance least cost path to all other nodes. Thank you.